What the intermediate value theorem says is this. If an airplane takes off and flies to a height of 10,000 feet, there is a distinct moment in time when the airplane has been at every single height or elevation in between 0 and 10,000 in its flight. So that sounds obvious, and the intermediate value theorem does kind of feel like something that is stating the obvious, but what it means, again, is that there was a moment in time, we lost the front. There was a moment in time when it was exactly 5 feet off the ground. There was a moment in time when it was exactly 20 feet off the ground. There was a moment in time when it was exactly 9,874 feet, 0.2 off of the ground. So here's what the intermediate value theorem, or the IVT, actually says symbolically. If f of x is continuous, and as soon as you see that word, you should be thinking about the three conditions of continuity that the point exists, that the limit exists, and that the point is equal to the limit. If f of x is continuous on an interval from a to b, and by the way, take note that we are including a and we are including b, and also another condition, f of a does not equal f of b. So all that means is that these heights are different. This would be the height of f of b, and this guy would be the height f of a. So assuming that those values are different, then what the theorem says is that for every value that we're going to call m that lives in between f of a and f of b, so remind yourself that f of a and f of b, these are y values. So what we're saying is that every m in between f of a and f of b, so every vertical value in between f of a and f of b, there exists at least one value that here we're going to call c, such that f of c is equal to m. So a couple things to be aware of. C is an x value. So that means that c is a number that lives in between a and b. And what we're saying is that the output value when the input is c will equal m. So if we look at our picture that we've drawn, that's what we're going to try to show right now. We're saying that somewhere on the graph there's a value corresponding to our value c. So such that when we plug c into the function, we get the output value of m. This is the intermediate value theorem in a more formal way than my airplane picture. So to be clear, it's saying that every single value of m, so every single number that's in between f of a and f of b, so there and 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 there, all of those values can be corresponded to values of c in between a and b. All right, so real fast, another way to talk about the intermediate value theorem is by thinking about human degrowth. So what it means, again, is that there is at least one moment in time when this person is exactly this tall. I don't know how tall that is, 2 feet, 3 feet. There's exactly one moment in time when this person is this tall, and this makes sense, right? In order for us to get to this height, we've got to pass through the nanosecond in time when we are whatever this height is. And the piece that I'm pointing out here is that the intermediate value theorem says that there's at least one moment in time. There's at least, for every height m, there's at least one corresponding c value. So for us here, our corresponding c value would be this moment in time. But then you'll notice that there's going to be another one as well. As this person shrinks, there's another moment in time when he's that exact same height. So that would be our other value of c. So the intermediate value theorem is an existence. It is an existence theorem, which means that it speaks to the existence of something. It speaks to the nature of something. It doesn't really tell you what to do with it. It just tells you this is an observable reality. So what I want to look at next is what kind of situations are you going to find yourself in with needing to know the intermediate value theorem? Okay, let's look at another example. In this question, we are to explain why this function has a 0 in the given interval. So the function is x cubed plus 3x minus 2, and our interval is from 0 to 1, and it says explain why the function has a 0. We're going to use the intermediate value theorem to explain this. What we're going to do is, this is like our a, and this is like our b. So we're going to just go ahead and find f of a, and we're going to find f of b, and let's see what that does for us. So when we plug 0 in and evaluate f of 0, we end up with this statement, which is equal to negative 2. And when we evaluate f of b, or in our case f of 1, we end up with 1 cubed plus 3, which is 4, and 4 minus 2 is 2. So when x is 0, we're down here at negative 2. And when x is 1, we're up here at positive 2. So here's what we know. This function is a continuous function. There's no discontinuities because it's not a rational function. It's a polynomial. It's a cubic polynomial. And we do not know what it looks like. It could look something like this, or it could look something like this, or it could look like this. We don't know. We don't know. But what we do know is that it's continuous. And so what we know is that by the intermediate value theorem, if we're trying to find a height of 0, or in other words, if we're trying to identify our 0, we know that there must be some moment in time in our interval from 0 to 1, at which point we cross over. There is no way to get from our first point to our second point without crossing over the x-axis and subsequently generating an x-intercept or a 0. So we can make this statement that because f of x is continuous, there must exist a 0 by the intermediate value theorem. Alright, last example here. This one says verify that the intermediate value theorem applies and find the value of c guaranteed by the intermediate value theorem for this function between 0 and 3. So first of all, we got to ask ourselves, does the intermediate value theorem apply? For the intermediate value theorem to apply, the function needs to be continuous, which this function is continuous. We have a quadratic. All quadratics are continuous. And we are on a closed interval from 0 to 3. So we are rocking and rolling. We're going to start by identifying f of 0 and f of 3. So when we evaluate these expressions here, we get 8 for f of 0, and then f of 3 is going to be 9 minus 18 plus 8, which will give us negative 1. So let's just make a quick picture of where we're at. We're on a closed interval from 0 to 3 in the x direction. When we plug 0 in, we get 8, and that point would be represented there. And when we plug 3 in, we get negative 1, and that point would be represented right there. So we know that by the intermediate value theorem, somehow, some way, we've got to cross over. I don't know if that's what the graph looks like, but somehow we're going to cross over. So this this condition here, it says where f of c is equal to 0, what this means is that there is some c, or some input value along the x-axis, such that the output is 0. In other words, it is a 0, and our job is to find that 0. So to do that, we're going to set our equation equal to 0. and we have a quadratic equaling 0. We're going to factor this thing. And the factors of x squared minus 6x plus 8 are going to be x minus 4 and x minus 2. So there are two zeros. One is at positive 4, and the other is at positive 2. So now I can fill this graph in a little bit more accurately. One's at 2, one is at 4. So my quadratic is looking something like this. So the question is, what value of c is guaranteed by the intermediate value theorem, which always happens on a closed interval? And on this closed interval, there's only one correct answer. Even though I have 4 and 2, 2 is the only answer that is within the closed interval from 0 to 3. Therefore, c is equal to